A single flash of lightning can toast 100,000 slices of bread. Read that again. One bolt, one instant, 100,000 slices. That number doesn't just sound exaggerated. It sounds physically impossible, like someone took a real fact and multiplied it by 1,000 to fill a YouTube thumbnail. But they didn't multiply it. And the truth about what's actually happening inside that flash is far stranger than the number itself. Here's what you see when lightning strikes. A white line against a dark sky, a crack that seems to come from everywhere at once, a flicker that's gone before your brain finishes processing what happened. Your eyes tell you it lasted a fraction of a second. Your ears tell you the sky just split open. Then silence. But inside that fraction of a second, inside that crack, something almost incomprehensible is happening at the atomic level. A single lightning bolt carries between 1 and 5 billion joules of energy. A joule is the standard unit of energy in physics, roughly the amount needed to lift a small apple 1 meter off the ground. Now picture 1 billion of those, released not over minutes or hours, but in roughly 30 microseconds. That's 30 millionths of a second. During that instant, the power density at the core of the bolt exceeds the output of a small electrical power plant. The air inside the lightning channel reaches approximately 30,000 Kelvin. That's around 53,000 degrees Fahrenheit. For context, the surface of the sun, the star keeping your entire planet warm enough to sustain life, is about 5,500 Kelvin. A lightning bolt is more than 5 times hotter than the surface of the nearest star. So hot that the air doesn't just warm up, it detonates. The instantaneous heating causes gas molecules to expand faster than the speed of sound. That violent expansion is what produces thunder. Thunder is not a separate event from lightning. It is the sound of air being torn apart by heat. Martin Newman understood this better than almost anyone alive. Newman, a physicist at the University of Florida, dedicated his career to studying the lightning discharge. His 1987 book, The Lightning Discharge, remains one of the most cited works in atmospheric electricity research. Newman's work revealed that what you perceive as a single bolt is actually a cascade of multiple events. A faint, invisible tendril of electricity called a stepped leader crawls downward from the cloud in 50-meter jumps, probing the atmosphere for a conductive path. When it connects with a rising streamer from the ground, a return stroke, the brilliant flash you actually see, rockets upward at roughly 1/3 the speed of light. This cycle can repeat 3, 4, even 5 times within a single flash. Each return stroke reuses the same plasma channel. That's why lightning appears to flicker. There's also the smell. After a lightning strike, many people report a sharp, clean, metallic scent in the air. That's ozone, O3, a molecule made of 3 oxygen atoms instead of the usual 2. Lightning rips apart normal O2 molecules in the atmosphere, and the freed atoms recombine into ozone. That electric smell after a thunderstorm is literally the chemical footprint of billions of molecular bonds being broken and reformed in a fraction of a second. And then there are fulgurites. When lightning strikes sand, the temperature is so extreme, over 30,000 degrees, that it melts the silica grains on contact, fusing them into hollow glass tubes that can extend several feet into the ground. Fulgurites look like frozen lightning captured in glass. They're a physical record of the exact path the current traveled through the Earth. Some specimens have been found over 15 feet long. The energy required to melt that much sand in a fraction of a second gives you a visceral sense of the raw power involved. Now back to the toast. A standard 2-slice toaster draws about 1,000 watts and runs for roughly 2 minutes to brown bread evenly. That's approximately 120,000 joules per cycle. If a lightning bolt delivers around 1 billion joules, and you could somehow channel all of that energy into your toaster, pure fantasy. But stay with the math. You'd get enough energy to toast somewhere around 8,000 slices in one flash. But that's the conservative figure. The most energetic bolts carry closer to 5 billion joules. Factor in the total electrical energy across the full discharge, ground current, electromagnetic radiation, every return stroke, and the number climbs much higher. Under the most generous calculations with the largest recorded bolts, you approach the headline figure, 100,000 slices. The reason the math works isn't that lightning contains some mystical superfuel. It's that your toaster is slow on purpose. A toaster deliberately meters energy over 2 gentle minutes. Lightning dumps it all at once. Same fundamental energy, wildly different delivery speed. And that is exactly what makes lightning so destructive. It's not the total energy that kills, it's the rate of delivery. A single bolt can carry up to 30,000 amps of current. The outlet in your kitchen delivers 15 to 20 amps. Lightning pushes roughly 1,500 times more current through the atmosphere than your home wiring pushes through copper, in less than a second, through a gas that is normally one of nature's best insulators. So how does electricity flow through something designed to block it? The mechanism is called dielectric breakdown. Air is an insulator because its molecules don't normally allow electrons to flow freely. But when the voltage difference between a thundercloud and the ground climbs high enough, we're talking hundreds of millions of volts, the electric field becomes so intense that it rips electrons directly off air molecules. The air transforms into plasma, an ionized state of matter that conducts electricity beautifully. Once that plasma channel forms, every ounce of stored electrical potential in the cloud rushes through it simultaneously. Think of it like a dam breaking. The water was always there. The pressure was always building, but once the wall cracks, everything flows at once. Lightning is the crack. C.T.R. Wilson was among the first scientists to prove this with measurements. Wilson, a Scottish physicist, won the Nobel Prize in 1927 for his invention of the cloud chamber, but his lesser-known research involved measuring the electric fields inside thunderstorms during the 1920s. He established that storm clouds develop massive internal charge separations, billions of coulombs of charge separated by kilometers of air. His work laid the scientific foundation for understanding how the atmosphere generates lightning in the first place. Without Wilson's measurements, we might have spent decades still debating whether lightning was even an electrical phenomenon. And here's the part that should make you shift in your chair. The Earth gets struck by lightning approximately 100 times every second. That's roughly 8.6 million strikes every single day. Most hit open ocean or uninhabited land. But about 2,000 people are killed by lightning strikes each year worldwide, and tens of thousands more survive with permanent injuries, neurological damage, cardiac scarring, chronic pain, hearing loss, memory impairment. Roy Sullivan, a U.S. park ranger at Shenandoah National Park in Virginia, was struck by lightning 7 separate times between 1942 and 1977. He survived all 7. The probability of being struck once in an 80-year lifetime is roughly 1 in 15,000. The probability of being struck 7 times is, mathematically, essentially 0. And yet it happened to one man. And lightning doesn't need to hit you directly. A significant portion of lightning injuries come from ground current, the electrical charge that radiates outward through the earth when a bolt strikes nearby. You don't have to be the target. You just have to be standing close enough to where the current enters the ground. In open terrain, that danger radius can extend over 30 meters from the strike point. So what would actually happen if you tried to physically toast bread with a lightning bolt? You couldn't, not with any technology that currently exists. The energy arrives too fast in too concentrated a form and through a medium, superheated plasma that would obliterate any physical structure before the energy could be captured. A toaster connected to a lightning bolt wouldn't toast the bread. It would vaporize the toaster. The bread, the counter, a meaningful portion of the kitchen. The challenge of lightning energy isn't the quantity. There's more energy in one bolt than your house uses in an entire month. The challenge is time. Nature compresses the output of a small power plant into a channel thinner than a pencil, for less than a second, through a medium that ceases to exist the instant the energy passes through it. That's not a power source, that's a bomb shaped like electricity. And yet we keep trying to harness it. Nikola Tesla, working at his Colorado Springs laboratory in 1899, built a massive magnifying transmitter that could generate artificial lightning indoors. Tesla believed the atmosphere held essentially unlimited free energy. He was right about the energy. He couldn't solve the storage problem. Over a century later, nobody has. Modern research continues to reveal how much we still don't know. The European Space Agency's Atmosphere-Space Interactions Monitor, mounted on the International Space Station in 2018, studies powerful electrical discharges above thunderstorms that scientists barely understood 2 decades ago. Blue jets shooting upward into the stratosphere. Red sprites flickering 50 miles above the clouds. Elves expanding rings of light at the edge of the ionosphere. Lightning, it turns out, doesn't only go down. Some of it reaches upward into near space. The more we study lightning, the more extraordinary it becomes. You thought it was just a flash in the sky, a bright line to count seconds against, something dramatic but simple. But inside that flash is a cascade of physics so violent it tears apart air molecules, generates electromagnetic pulses detectable from orbit, fuses sand into glass, creates ozone you can smell, and carries enough energy to run every toaster in your neighborhood for a year. Every time you glance up during a storm and see that flicker on the horizon, you're watching more raw power in a fraction of a second than your entire house will use in months. And the next time you slide 2 slices of bread into a toaster and wait 2 patient minutes for them to turn golden brown, remember this. You are using the exact same fundamental energy that lightning uses. You're just using it gently. Lightning doesn't do gently. The universe gave you the same fuel. You just chose to make breakfast with it instead of setting the kitchen on fire.